Okay, guys, welcome. So today we're going to talk about ordered pairs. Now, in this course, when we consider an ordered pair A comma B, we're going to mean the set where we have A and then the other set A comma B, and the set containing those two sets. Now, this is one of the many definitions that you can use for an ordered pair, but we essentially just need our definition of ordered pair to satisfy that if two ordered pairs are equal, then their first coordinates are equal and their second coordinates are equal, right? So there are many different ordered pair definitions that you could use to make this true, but we just require that as whichever definition that you go by, we need it to ensure that the first coordinates are equal and the second coordinates are equal. Now, if we have two sets A and B, then we consider A cross B to be the Cartesian product of A and B. And what this Cartesian product is that it's going to consist of all ordered pairs where the first coordinate is from the set A and the second coordinate is from the set B, right? So A cross B is the set of all ordered pairs A comma B, such that A is in A and B is in B. Now, if we want to cross a set with itself, we usually use powers, right? So we would say that A squared is like A cross A, and then in general, A to the n would be like A cross A n times. So let's look at an example. So for a set A, we have 1, 2, 3, and for a set B, we have x, y. So A cross B is going to be a set of ordered pairs, of course, where the first coordinates from A, so I got to have either 1 comma x or 1 comma y. But then I could have 2 comma x and 2 comma y. And then I could have 3 comma x and 3 comma y. All right, so it looks like we get 6 possible elements there. And of course, if this brings us to a theorem that if we have finite sets A and B, then the number of elements in their Cartesian product is the same as taking their individual cardinalities and multiplying them together, right? And we'll do a quick sketch of the proof here. So we're going to suppose that A is A1, A2, and we'll say that it has n elements. Okay, and then we'll say that set B is B1, B2, and we'll say that it has m elements. Okay, so now let's consider ordered pairs with first coordinate A1. Well, to select an element from set B to be the second coordinate, A1 has m choices for a second coordinate. Right? So there are m ordered pairs with A1 as its first element. Right? Well, now we just repeat the argument for A2. So once this goes down, okay. So now we repeat for A2. And you're going to have m ordered pairs with A2 as its first element. Now, if you repeat this for all n elements, you're going to have m times m times m times m, where you have n of these things. Or I shouldn't say that. No. Not times. It's plus, right? because I could take the m elements for A1 plus the m elements for A2 plus the m elements for the last one. And here there are n of these m's. So of course, this is just multiplication. This is just n times m. All right, and that's sort of the idea behind the proof. And of course, this leads us to what's called the multiplication principle, which says that if you have some event E1, which can happen m ways, and another unrelated, uncorrelated, which we sometimes call independent, event E2 can happen in n ways, then the number of ways that they two ways can happen is m times n. We take their product. All right, so that concludes this video on the idea of ordered pairs. I hope you enjoyed, and I will see you next time.